Today we're going to determine if the sum as n goes from 2 to infinity of sine of n over the natural log of n converges or diverges. And this may not seem super interesting, but it will allow us to look at a lesser known convergence test, as well as notice that this can easily be adapted to a large family of similar series. And so what is that lesser known convergence test? It's called Dirichlet's test. And it says if we've got two sequences of real numbers, I've labeled them a sub n and b sub n, satisfying the conditions that a sub n is monotone, either increasing or decreasing, and the limit of a sub n is 0, and finally, the nth partial sum, so the capital Nth partial sum, is bounded above by some real number. And this real number is the same for all natural numbers capital N. In other words, all of the nth partial sums are bound above by some number. And you might say, well, this seems like it means that the series b sub n converges, but in fact it does not mean that because it could have some sort of oscillatory behavior. Okay, so if you've got those three conditions, then the sum as n goes from 1 to infinity of a sub n times b sub n ends up converging. Okay, so we're going to prove this, and then we're going to see that this implies a better known convergence test, and then we'll jump into our problem. Okay, so for our proof, we're going to look at the case when the A series is decreasing. Although, notice that if the A series is decreasing, if you multiply it by -1, then it'll be increasing. So in fact, we only need to look at one of those. Okay, so without loss of generality, keeping that in mind, assume, like I said, that the A sequence is decreasing. So in other words, we have an plus 1 is less than or equal to a sub n for all natural numbers n. And I guess I have that it's weakly decreasing here, but that's enough. Okay, nice. And now let's jump straight into our series. So we've got the sum as n goes from 1 to infinity of a sub n times b sub n. And then we're going to write this as a limit of partial sums. So this is going to be the limit as capital N goes to infinity of the sum as n goes from 1 to capital N of a sub n times b sub n. But now from here we're going to use something called summation by parts. I actually proved that on the channel a long time ago. If you can find that video, maybe post the title in the comments. Okay, so that allows us to take this term right here, which is a bit hard to deal with, and turn it into something that's a little bit easier to deal with. And that'll look like this. So we'll have a sub capital N, so that's the top A term. And then we'll have the sum as n goes from 1 to capital N of the b sub n terms. Then we'll subtract from that the sum as n goes from 1 to capital N minus 1 of this difference an plus 1 minus an times a sum which is inside of this other sum. So it'll be the sum as k goes from 1 to lowercase n of b sub k. So I guess it's important to notice that this sum right here is inside of the n sum. Okay, so now we're going to do as much simplification as we can in this first step. So notice that this term right here is most definitely bounded. That was like one of our assumptions over here. Furthermore, we know that this a sub capital N term tends off towards 0. So if this thing is bounded and this thing tends off towards 0, that means their product also tends off towards 0, which means our sum in question is actually only dealing with this last term right here. Okay, so now let's rewrite this a little bit. So let's look at the sum as n goes from 1 to infinity of the absolute value of a sub n times b sub n. So spoiler alert, we'll actually show that this thing absolutely converges. But then if it absolutely converges, it converges and we'll be good to go. Okay, so let's see. This will be equal to the limit as capital N goes to infinity of, well, we'll have the absolute value of the sum as n goes from 1 up to capital N minus 1 of, I'm going to switch that there to an minus an plus 1. And that is done just by taking this minus sign inside. So I think that's pretty clear. But notice that this thing is bigger than or equal to 0 based off the fact that an plus 1 is less than or equal to an. Okay, so anyway, and now inside of that we have the sum as k goes from 1 to lowercase n of b sub k. Great. And now we're going to apply the simple triangle inequality. So that means all of this will be less than or equal to, well, we'll have this limit as n goes to infinity, and then we can bring the absolute value inside. So that'll give us the sum as n goes from 1 to capital N minus 1 of, let's see, this term right here, an minus an plus 1. You might say, well, where'd the absolute value go for there? Well, I ordered those so that they're definitely non-negative, so we don't need that. And then we'll have the absolute value of this sum as k goes from 1 to lowercase n of b sub k. Oh, but check it out. This term right here is bounded above by some number m. That's in our assumption of Dirichlet's series. So like I said, that's less than or equal to m. So that makes this whole thing less than or equal to m times the limit as n goes to infinity of the sum as n goes from 1 to capital N minus 1 of an minus an plus 1. But notice that's a pretty simple telescoping series. So what do we have? Well, we save the n equals 1 term because that's only appearing in this a sub n. It doesn't appear in the a sub n plus 1. And then we'll have an a capital N term, and that only appears in the a sub n plus 1. So anyway, this looks like m times the limit as n goes to infinity of a1 minus a sub capital N. But now we can apply this rule over here, that sequence has a limit of 0, meaning this whole thing is m times a1. But then if we can bound a series of positive terms, which these are positive terms because we've got the absolute value above by some number, we know that this converges. And I guess we know that by the monotone sequence theorem, because the partial sums here are definitely increasing because we have positive terms. I guess I should say non-negative terms. And then they're bounded above by that number over there. So anyway, this thing converges, which means our series absolutely converges, which means the series we're interested in converges. Okay, so let's see how this implies the alternating series test. Okay, for our proof, we're going to look at a special case, and that'll be the case when an is monotonically decreasing. But the other case is really easy to prove if you just multiply the whole thing by -1. Okay, so that means that we need to suppose that a sub n plus 1 is less than or equal to a sub n for all natural numbers n. Okay, great. And then let's maybe consider this. So we've got the sum as n goes from 1 to infinity of an bn. And so that'll be equal to the limit of partial sum. So we've got the limit as capital N goes to infinity of the sum as n goes from 1 to capital N of an bn. Now we're going to apply something called the summation by parts formula. And this is kind of like the integration by parts formula, but for sums. And I've proven this on the channel before. If you can find it, maybe post the title of the video in the comments. Okay, so that'll allow us to take this and rewrite it as follows. So we have the limit as capital N goes to infinity of a sub capital N times the sum of lowercase n going from 1 to capital N of b sub n, and then minus this sum as n goes from 1 to n minus 1 of an plus 1 minus an times the sum as k goes from 1 to n of b sub k. So notice that b sub k sum is within this sum right here. Okay, so let's start off with some simplification. So we know that this term is bounded. That's one of our assumptions over there. So that's a good place to start. And then we know that the limit of these terms is 0. The a terms tend to 0. That's also one of our assumptions. But putting those two things together, that means that this whole first term simply goes to 0, which means we can write this as the limit as n goes to infinity of, let's see, we'll have the sum as n goes from 1 to capital N minus 1. Let's bring this minus sign in, and we have an minus an plus 1. And inside of that, we have the sum as k goes from 1 to capital N of b sub k. And now let's consider this new series which is appearing inside of this limit, and we'll consider this on its own. So let's bring this over here. So I'm gonna maybe write that as a full sum. So we've got this sum as n goes from 1 to infinity of an minus an plus 1 times, I'm gonna write this as the absolute value of the sum as k goes from 1 to capital N of b sub k. Great. So if we show this converges, then we know this object also converges, which means our sum converges. Okay, so how can we do that? Well, notice this is a series now with all positive terms. So if we can bound it above by something that converges, then we're good to go. So let's see what we can bound it above by. Well, let's note that an minus an plus 1 times this sum as k goes from 1 to n of bk, an absolute value, is most definitely less than or equal to an minus an plus 1 times our capital M, where that capital M is the bounding number for the bk sum that we assumed over here. Now, if we can show that this thing converges, then this thing converges, and thus this thing converges over here. So can we show that thing converges? Well, in fact, we can, and we can do it by looking at the limit of partial sums again. So let's look at M, and then the limit as capital N goes to infinity of the sum as n goes from 1 to capital N of an minus an plus 1. But now this is just totally built to have some sort of telescoping action. The only an term that won't be obliterated by an an plus 1 term is the first. And the only an plus 1 term that won't be obliterated by the a term is the last. So in fact, we can write this as m times the limit of capital N going to infinity of a1 minus an plus 1. But now that an plus 1 term goes to 0 by our assumption over here. So this limit is m times a1. So what does that mean? So that means that the sum defined by these terms converges, but in turn by the comparison test, the sum defined by these terms converges. But then if the sum defined by these terms converges, then this sum converges. Then this limit converges and our original sum converges, and we have it. Okay, so now that we've done this, let's look at the maybe more standard convergence test that this easily implies. So of course the alternating series test is way more well known than Dirichlet's test, but it follows very, very quickly. So let's recall what it says. If we've got positive terms an that are decreasing and their limit is 0, then the sum as n goes from 1 to infinity of minus 1 to the n, a sub n converges. And all we need to do is use Dirichlet's test over here with b sub n equals minus 1 to the n. So the partial sums there will very clearly be bounded above by 1 or 2, depending on if this inequality is strict or not. Okay, so now let's jump into our main question. Okay, so the first thing that we need to do is figure out who's playing what role here. So of course, one of our sequences will be the sine of n, and the other one will be 1 over the natural log of n. Well, which one of those is monotone and has a limit that's 0? Well, it's 1 over the natural log of n. So let's write that down. So let's note that the natural log of n plus 1 is clearly bigger than the natural log of n. The natural log function is well known to be increasing, but that means that 1 over the natural log of n plus 1 is less than 1 over the natural log of n, and they're both bigger than or equal to 0. And so the fact that they're bigger than or equal to 0 follows from the fact that we're starting here at n equals 2. Okay, so that's good. And then also we know that the natural log of n goes to infinity as n goes to infinity. So that's kind of well known as well. But that means that the limit as n goes to infinity of 1 over the natural log of n is simply equal to 0. So all of this is to say that we can use the natural log of n, or I should say 1 over the natural log of n, as our a sub n sequence. Okay, so now let's look at our b sub n sequence. So let's maybe write it right here. Let's consider the following thing. And that is the sum as n goes from 2 up to capital N of the sine of n. So that needs to be bounded. Okay, so how can we show that's bounded? Well, it's actually not quite as hard as it might seem if we simplify this sine function using maybe some angle sum and difference formulas. And so in particular, we'll use the fact that the cosine of n plus 1 is the cosine of n times the cosine of 1 minus the sine of n times the sine of 1. So that's the angle sum formula for cosine. And also the cosine of n minus 1 is the cosine of n times the cosine of 1 plus the sine of n times the sine of 1. That's like an angle difference formula. But now from here, we could maybe subtract these two equations to cancel out the cosine of n terms and then solve, and you'll see that the sine of n can be rewritten in this kind of crazy way. 1 over 2 times the sine of 1 times cos n minus 1 minus cos of n plus 1. Okay, nice. So now let's put that up here. So this is in fact equal to 1 over 2 times the sine of 1. And then we'll have this sum as n goes from 2 up to capital N of this cosine of n minus 1 minus the cosine of n plus 1. Okay, nice. So now let's investigate that. And maybe instead of splitting it apart and re-indexing, let's just write the first couple of terms. I think that maybe gives us some intuition. So this is going to be 1 over 2 times the sine of 1 times. So let's see, the n equals 2 term will be the cosine of 1 minus the cosine of 3. And then we'll add to that the n equals 3 term. So that'll be the cosine of 2 minus the cosine of 4. And then the n equals 4 term. So that'll be plus the cosine of 3 minus the cosine of 5. And then let's also write the last two terms. So the capital N minus 1 term will be cosine of capital N minus 2 minus cosine of capital N. So like I said, that's the capital N minus 1 term. And then the capital N term will be cosine of n minus 1 minus the cosine of n plus 1. Okay, good. And now let's notice that we can visually see some things canceling. This cosine of 3 will cancel with this cosine of 3. It stands to reason that this cosine of 4 will cancel with something out there, and that cosine of 5 will also cancel. But notice that cosine of 1 and cosine of 2 seem to survive. Then the same thing is going to happen towards the end. So this cosine of n minus 1 will get canceled by something further back. So will the cosine of n minus 2. But the cosine of n and the cosine of n plus 1 will not cancel. So here we have, this is 1 over 2 times the sine of 1 times, let's see, we have cosine of 1 plus cosine of 2, and then minus cosine of capital N minus cosine of capital N plus 1. So let's see, if we were to take the absolute value of this and then maybe use the triangle inequality, then at worst, all 4 of those terms will give us a 1, which means this is pretty clearly bound above by 2 over the sine of 1. Okay, so we've got it. We've got, let's see, our partial sums are bound above, and then our 1 over natural log terms are monotone and they have a limit of 0. So putting those two things together means that our series actually converges. Then let's maybe talk about the whole family of series that converge because of, well, this last calculation right here. So we can use this calculation down here to argue that if sequence AN is monotone and its limit is 0, then the sum as n goes from 1 to infinity of a sub n sine of n converges. And that's simply because this partial sum of the sine terms is bounded above, and then apply Dirichlet's test. So in particular, this harmonic looking series with a sine n on the top converges, which is another series that shows up from time to time. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.